So we move to our last speaker of this session, Professor Ronald Brinkgreve. And I will give a very brief introduction before starting. He's a part-time distinguished scientist at Países, and he's advisor and initiator of geotechnical software-related research activities there. He has been director of geotechnical research at Bentley System and manager of the Compiti Center for Geoengineering. He's also a part-time associate professor at the geoengineering section of the Faculty of Civil Engineering and Geoscience at Delft University of Technology. He gives courses on considerate modeling and numerical methods and supervises master and PhD students. As a researcher, Ronald has contributed to the scientific development of Países software, and he has published many papers on the use of considerate models and numerical methods in geotechnics. As a lecturer, Ronald has been involved in several international courses and in company training on backgrounds of the Países software, considerate models, and numerical methods. He maintains a large international network of contacts at universities, institutes, and the industry, participated at various boards and committees, and he in 2022 the Países team, which with the participation of Ronald, was awarded the Outstanding Innovator Award of the International Society of Soil Mechanics and Geotechnical Engineer. Ronald, thank you very much for accepting this invitation, and the floor is yours.
Thank you very much. Do you see my screen? The right screen? Perfect. Thank you very much, dear colleagues and friends. My presentation today is entitled Numerical Modeling of Tunnels and Shafts in a Data-Driven Environment. And I would like to thank the organizing committee for inviting me to deliver this presentation. And also thanks to my Sequent colleagues for helping me in collecting and preparing the information for this presentation. Here's an overview of my presentation. After a short introduction, I will highlight some advances in digital and numerical modeling, including pre- and post-processing, constitutive modeling, and automation. I will show two examples from engineering practice in which numerical modeling and automation has led to optimization in tunneling projects. Then I will briefly talk about the current trend of connected or integrated workflows and digital twins. In the second part of my presentation, I will present a future outlook on numerical modeling in which data and artificial intelligence are going to play a major role. I will give 4 examples on the use of machine learning in relation to numerical modeling. I will end with some conclusions. In the Netherlands, much research related to the practical construction of bored tunnels in soft soils has been performed in the 90s of the previous century. As a result, the first TBM tunnel in the Netherlands, the second Heinenoord tunnel, opened in 1999. Since then, more than 10 bored tunnels were constructed. The most recent TBM tunnel is the Corbelow tunnel in the Rijnland route near Leiden, which opened last year. For all these tunnels, numerical modeling has been performed as part of the design process. In preparation of this presentation, I dived into the history of numerical modeling of tunnels and shafts in practical applications and found this example from 1993. The picture shows a finite element model for the construction of the TBM tunnel for the North-South Metro line in Amsterdam. This involves a 2D plane strain finite element model composed of a limited number of 50-node triangular elements. The volume loss due to TBM tunneling was simulated using contraction of the tunnel lining, as Angelo already mentioned. The right-hand plot shows the rotated principal stresses in the ground, indicating arching around the tunnel. 8 years later, it was already practically possible to model TBM tunnel construction using a 3D finite element model. The model shown here was created for back analysis of the second Heinenoord tunnel near Barendrecht. The deformation around the tunnel was modeled using a combination of 3D lining contraction and ground pressure modeling, followed by the installation of the final tunnel line. You can see how a settlement trough is formed and how every advancement step contributes to the surface settlements. Fast forward to 2017, when 3D finite element modeling of tunnels and shafts and the interaction with surrounding structures in an urban environment has become quite feasible and common practice. The model shows a tunnel with reinforcements constructed according to the sequential excavation method and its influence on the surrounding structure. MIA, or BIM, was introduced, offering new capabilities for integrated digital workflows. Now, in 2024, the new paradigm is digital twins. A digital twin is a digital copy of a project or asset, such as a tunnel or any kind of infrastructure. It makes all related information securely available for all stakeholders involved. A digital twin does not only cover the entire construction process, from preliminary design to project delivery, it also facilitates operation, maintenance, and retrofit all the way until the end of lifetime. 3D numerical modeling and finite element analysis as part of the design process can be fully integrated in a digital twin environment. Over to some advances in digital and numerical modeling. Looking at the development of finite element modeling capabilities over the last decades, they can be categorized into geometric modeling, constitutive modeling, structural elements, post-processing, and automation. I will subsequently demonstrate some of these developments, such as a tunnel designer for creating tunnel geometries, constitutive models for soil, rock, and shotcretes, special elements for anchors, rock bolts, bore poles, and cables, and I will mention tools for post-processing and automation. In particular, the programming language Python, with all its available libraries, has proven to be extremely useful in automation. The import of CAD models of tunnel contours for numerical analysis is often problematic, since CAD models may provide inconsistent geometries. The use of a tunnel designer in the finite element software is not only useful to create a consistent tunnel geometry, it also facilitates the generation of structural components as well as the installation phases. In this way, a consistent numerical model can be created that allows for a realistic simulation of the tunnel construction process, both for TBM type of tunnels as well as for tunnels following the sequential excavation. Significant advances have also been achieved in terms of constitutive models for soils and rocks. Besides the well-known modified Chemclay model and hardening soil model with small strain stiffness, more advanced models are nowadays available that incorporate specific features of soil and rock behavior. Such features may include anisotropy, strain softening, unsaturated soil behavior, swelling, and creep. Note that strain softening behavior requires the use of a so-called regularization technique to reduce the inherent mesh dependency that would otherwise make the results unreliable. A special rock modeling feature is a discrete fracture network generator. This is not a constitutive model, but a tool to generate discontinuity elements with a separate failure criterion in the finite element mesh based on a stochastic distribution of fracture orientation and sizes. One of my TU Delft students, Vasilios Skordilis, created his own 2D DFN generator and investigated different failure criteria for discontinuity elements. Unfortunately, there is no time to go into the details of all these models, but more information is available in the various publications from researchers in our group. Some references are given at the end of this presentation. A special constitutive model has been developed for shotcrete. This model deals with the hardening of the fresh shotcrete on the short term, as well as the nonlinear stiffness and strength properties in compression and tension on the longer term, including strain softening and creep. The use of such an advanced model may be beneficial in the design process. Its nonlinearity will generally result in lower stress concentrations, and as a result, less reinforcement is needed in the design of a tunnel lining than what would otherwise be needed when using a simpler model. Structural elements have been developed to account for various types of anchors, rock bolts, fork bolts, and cables in the numerical model. These elements make use of the embedded beam concept, where a line element can arbitrarily cross a continuum element representing the surrounding soil or rock. Apart from its structural properties, the line element also incorporates a special type of interface that accounts for a realistic interaction and bonding with the surrounding soil or rock. These structural elements can be conveniently and consistently incorporated in the numerical model via the tunnel design. Shotcrete tunnel linings are generally reinforced by steel bars or meshes. The combination of both is typically modeled as a composite shell in a finite element model. The equivalent shell properties can be calculated with help of a pre-processing tool, while the mobilized capacity of the separate components can be assessed using an enhanced post-processing tool. The resulting picture shows where the actual combination of structural forces of the shotcrete and the steel reinforcement lies within the corresponding capacity diagrams. Automation helps making the numerical modeling process efficient and less error-prone. Modern finite element software works with a command line interface that allows predefined command scripts to be executed. The executed commands are logged, and the logs can serve for quality control purposes. An application programming interface, or API, allows external software to interact with the numerical model. An external Python program can be written to send commands and extract results, thereby controlling the entire modeling and calculation process. The API does not only make the model creation more efficient, it also provides numerous possibilities for automated processes that would otherwise cost an immense amount of handling time from the user. Examples of such automated processes are parametric studies, sensitivity analysis, design optimization, probabilistic analysis, and the modeling of heterogeneity by means of random fields. And last but not least, it allows for connected and integrated workflows and the exchange of data within a digital environment, such as in BIM and digital twins. I will come back on this in a few moments. Now I will show two examples from engineering practice where numerical modeling is used to facilitate and optimize the tunnel design and construction process. The first example is a 3D back analysis of in-situ measurements for the South Toulon Tunnel in France. The full-phase excavation involves various types of reinforcement to ensure the tunnel stability in the difficult heterogeneous ground conditions. The reinforcement strategy was adapted and optimized based on the measurement data. The measurements were also used to validate the numerical back analysis model, which was used to gain more insight in the complex soil structure interaction behavior around the tunnel and its reinforcements. The graphs show the 3D settlement profile in longitudinal direction and in a cross-section in comparison with the measurements. costs. The numerical back analysis provided the following benefits to the project. It led to an optimization of the construction methodology, in particular with respect to the placement of reinforcement elements. It gave an improvement of the efficiency of the project, as well as the stability and safety during construction. Overall, it led to a reduction of project costs and risk. The second example is the automated analysis of a segmented precast concrete tunnel lining, or PCTL, using Python scripting. As can be seen from the pictures, not only the geometry of a PCTL tunnel is difficult to create in a finite element model, also the interaction properties between the lining sections require special attention. Manual model creation would lead to a tedious and error-prone process. A generalized and parameterized Python script was developed for the modeling of PCTL tunnel linings in the engineering practice. The script can be used to automatically create or generate tunnel geometries, segment interactions, loading conditions, and construction sequences for numerical analysis. The benefits of the Python script are multiple. It automatically generates complex tunnel geometries. It deals with the complex segment connections and their interaction properties without introducing modeling errors. It also handles the tunnel advancement and translates this into construction stages or calculation phases. Overall, it is a very efficient modeling tool for PCTL tunnels available for practical users. As promised, I will now take a moment to talk about connected workflows and digital twins. Data plays an important role in any projects. Connected workflows and digital twins are centered around data, typically stored in the cloud. A digital twin exists by the interoperability and exchange of data between different software packages. It is essential that the data is kept up to date as a single source of truth, such that all processes and results depending on these data are also kept up to date. Within a digital twin, geotechnical and geological data can be interpreted and processed into soil and rock strata and parameters. These data can be passed onto geological modeling software to create a 3D subsurface model. Sections from the subsurface model, together with structural data and components, can be further processed to create geotechnical and structural analysis models for performing design calculations. Results from these calculations can also be stored in the system. Moreover, sensor data and real-time observations stored in the system can be used for monitoring, back analysis, and optimization. All up-to-date information is presented in a structured and meaningful way for project management and decision-making purposes, and securely made available for any stakeholder in the project. As mentioned, a digital twin does not only cover the design and construction process, it also captures the continuously evolving state of a project from its concept and planning to design and construction, and following digital modeling and automation, it's clear that integrated twins are ready for the next step in tunneling and infrastructure projects. Now it is up to the industry to adopt digital twins and benefit from the connected workflow and instantly available project data, not only in new projects, but also for existing tunnels and other infrastructure. The remaining part of my presentation gives an outlook on the numerical modeling of tunnels and shafts in a data-driven environment in which artificial intelligence and machine learning will play a major role. As mentioned, data and up-to-date information is essential in any project. For tunneling projects, this may involve geometric and location data, ground data, structural data, materials and properties, including soil, rock, structural properties, measurement data from sensors and observations, elaborated data resulting from the interpretation of raw data and from the design process. The numerical modeling of tunnels and shafts needs such data and may benefit from a further enhancement of these data. Automation, as well as artificial intelligence and machine learning, may help to efficiently process these data and facilitate numerical modeling. In the following slides, I will demonstrate some concrete examples using AI and ML in numerical modeling. A first example where AI and ML can help numerical modeling is in parameter determination. We have developed a method for automated parameter determination, or APD, from cone penetration tests and other field tests in soil based on the graph method. The graph method is a form of artificial intelligence. It is used to create paths of correlations all the way from the core CPT parameters via intermediate soil properties to the final soil and model parameters. The green nodes are the parameters and the blue nodes are correlations or other equations. You can see, for example, that the relative density dr is obtained from 3 different correlations and subsequently used in other correlations to determine other parameters. We have collected hundreds of correlations and parameters in CSV files that are read by the system, including the conditions that apply to them. It is very important to obey these conditions in order to use the correlations appropriately. To determine all model parameters of the hardening soil small strain model requires a more extensive graph, but in principle, the whole parameter determination process is still transparent and verifiable. Users can follow how parameter values propagate through the system. Alternatively, an artificial neural network could be trained on the input and output parameters to provide model parameters for other cases. However, in this way, the parameter determination process is not transparent anymore and becomes a black box. Another way of determining soil and model parameters is, of course, based on lab testing data. Last year, one of my TU Delft students, Michael Stals, worked for his graduation project at Fugro on parameter optimization by numerically simulating lab tests and comparing the results with real lab testing data. He had access to a whole database with soil properties and lab test data. The stress-strain diagrams on this slide show the comparison between real triaxial test data and the numerical simulation. Left is before optimization and right after the optimization. In this way, the existing database was extended with optimized model parameters for the hardening soil small strain. He then used the extended database to see if a machine learning regression model could be trained to predict the model parameters directly from the basic soil properties. The diagram shows that using more soil properties improves accuracy, although the results are not perfect. The kernel-rich regression algorithm gives the best results in this case. Together with the automated parameter determination from field test data, as mentioned earlier, this could help overcome the lack of lab test data that is usual in an early stage of a project. Another use of machine learning is the determination of 3D soil layers to create a 3D subsurface model. After the interpretation and stratification of individual CPTs, which is common practice, a machine learning clustering algorithm, here K-means, is used to connect the corresponding layers across different CPTs. The clustering algorithm uses a signature of the soil layer as input data, in this case the core CPT parameters QC and RF, together with reference depth, as shown in the 3D diagram on the right. You can clearly identify the 7 clusters with corresponding corresponding parameter values that are formed by the algorithm. The clustering information is subsequently sent to a geological modeling package, in this case Leapfrog, to create a 3D subsurface model as a basis for numerical modeling. The third example of machine learning is surrogate modeling. A surrogate model is a data-driven model rather than physics-based that can provide instant results for a situation that can be described by a set of input parameters. A multivariate machine learning classification or regression model is trained on specific outcomes from different sources, such as field observations, but also more time-consuming numerical analysis can be performed to prepare the training data. It can replace numerical analysis in case multiple evaluations are required, for example, in parametric studies, design optimization, or probabilistic analysis. So far, surrogate modeling has been applied to relatively simple geotechnical problems, such as bearing capacity of foundations, stability of slopes and embankments, and deformation and forces in soil retaining structures, with variations in soil properties, geometry, and load configurations. The picture on the right shows a comparison of wall deflection from finite element analysis and surrogate modeling for an excavation project in London. It can be seen that the results from both models are very similar. The last example where AI and machine learning can be used is in conjunction with monitoring data, such as obtained from the observational method. AI and ML embedded in a cloud-based digital twin ecosystem can provide great opportunities to integrate the continuous flow of monitoring data with instant modeling capabilities into monitoring dashboards. This also enables the creation of early warning systems and decision support systems, allowing operators to take immediate action in case predefined values are exceeded or undesired scenarios are unfolding. That brings me to the conclusions of this presentation. Numerical modeling of tunnels and shafts has significantly advanced over the last decades. I have shown some examples of geometric modeling, constitutive modeling, structural elements, and automation that are available nowadays for efficient model creation and realistic simulation of practical tunneling projects. We also see that data has and will become more and more important. Numerical modeling integrates with data and other software applications into a cloud-based digital twin environment. A digital twin provides a seamless flow of data across all applications and secured access to a single source of truth for all stakeholders involved in a project. In the second part of my presentation, an outlook was given into the future. I have subsequently shown the use of AI and ML in parameter determination, 3D layering, surrogate modeling, and the use of monitoring data. AI and ML provide analysis opportunities that would otherwise be very time-consuming, such as parametric studies, design optimization, probabilistic analysis, and real-time back analysis. It facilitates the creation of monitoring dashboards and decision support systems, which can be of great help in risk management and cost control. The tunneling and infrastructure industry can highly benefit from such developments. I end my presentation with some references. Mr. Chairman, dear colleagues and friends, thank you very much for your kind attention.
Thank you for this very interesting presentation, Professor. We have time for a few questions. We invite the people attending that you can use the chat or the Q&A chat to ask some questions. Perhaps in the meantime, I can ask one myself. Regarding one of the last slides where you mentioned we know that the observational method is not particularly applicable when we have brittle materials, because let's say the amount of deformation required for collapse is generally quite small. But do you think that the incorporation, for instance, of artificial intelligence could improve the situation so that it can pick very subtle cues before we approximate to an instability condition?
Yeah, well, thank you for the question. Very interesting. Of course, we use measurements and we try to predict situations that we want to prevent, in particular failure situations. And depending on what kind of measurements you take, even with temperature, and I mean, there have been some cases where, or test cases where measurements were taken, not only deformation, pore pressures, but even temperature, where you see, for example, completely different applications like embankment failure, that before failure occurs, you see an increase of temperature. But if you take all the data into account, you can, and you take a lot of different cases where damage has occurred, including failure, then I'm sure that, with more data available for more cases, that at some point you can find a connection or a link between situations that have failed and situations that have not failed, where artificial intelligence and machine learning algorithms can actually predict whether such undesired situations could occur or are likely to occur based on the measurements that are taken. So I'm hoping that I'm answering your questions. I think, yes, machine learning and artificial intelligence can be of great use, especially with monitoring, in order to foresee if certain situations, undesired situations, would occur, and hopefully there is enough time to install mitigation measures to prevent that those situations will occur.
Perfect. Thank you very much. We have a question from Martin Ramirez. He asks, in the soft clays of the Valley of Mexico, the standard penetration tests give tool weight. So basically no blow count. In this case, how are the parameters obtained? Couldn't it be better to obtain the soil parameters with cone penetration test? Perhaps he's answering his own question.
Well, the question is clear. So far, we have used the cone penetration test, and I believe if you are dealing with the soft clay in Mexico City, then cone penetration test would be very well suitable. But I'm not an expert on Mexico clays and the soils around Mexico. But in the Netherlands, we have soft soils, and we do, in fact, always cone penetration tests for any project. And so over the year, but also in many other countries now, cone penetration tests get more and more popular. And so there are many correlations to start from the cone penetration test data, the QC, the RF, that relate to other parameters. And what we have done is to chain those correlations and to create paths of correlations all the way to the final model parameters. And of course, this is at some point is maybe not very accurate, but at least in an early stage of a project, when there is very limited data, cone penetration tests are cheap tests to perform, and they can be performed in an early stage of a project. And thereby, you can already start a preliminary design based on that test data. To be honest, we did not do this. We did not extend the tool that we have developed in Python based on standard penetration test, but we do have also incorporated in the meantime the dilatometer test. So our collaboration partner, the Technical University of Graz, they have good experience with the use of dilatometer testing data in the same tool that we are using for parameter determination. So hopefully that answers the question, and there I do see capabilities also for Mexico.
Thank you very much. Professor Amorosi wants to ask a question. Please, Professor.
Well, maybe it's more a comment. I very much appreciate the idea of getting everything from one single kind of test. But there's a point. technically speaking, a CPT test is run at the rate such that in a clay material, you are by definition in undrained conditions. So I guess that looking for correlation with two of the results with undrained parameters is fair. But then if you then want to extend the correlation to something that is in that context, not necessarily, you know, the key thing, the process is altered. For example, you want to get phi prime out of a CPT test run on a clay material. That it's a bit scary to me. And then my question is, shouldn't we be slightly careful in suggesting that based on a single set of tests, maybe not the ideal one and not the complete one can already start a design? Because at the stage of the starting of a design, you, especially on the geotechnical side, you have to be very, very, you know, sure of what you're doing. There's no much space to get backwards. So what is your answer on that?
Yeah, it's a very, very good question, Angelo. Well, I can call you Angelo. We know each other already for many years. Yeah, of course. But don't get me wrong. So what I'm suggesting is not to skip completely lab testing, and not at all. So of course, lab testing is needed in order to verify and calibrate your parameters and to come to final design parameters. There's no doubt about that. But especially, we all know that in an early stage of a project, there's very limited data, and yeah, lab testing might not be available. But still, companies are very eager to get started with a preliminary design. And in those cases, I think the use of such a tool based on field testing is very useful. Now, for the point of undrained, say, tests that are performed in a sort of undrained way or undrained test, still with undrained tests, for example, we can determine effective friction angle from a series of undrained triaxial tests where you plot the final results and then can still draw a critical state line through the end results to some extent. And so it's not impossible to derive drain parameters from undrained tests. But you are right. I mean, you have to be very careful with that. But still, I think in a situation where there's limited information and you want to get started with a design, a compenetration test, and well, honestly speaking, here in the Netherlands, we do everything with compenetration tests. This is amazing what people do with it, and this is also, I mean, not just in the Netherlands, but in many countries nowadays, the use of CPT data is very popular, and so I think it is more than just for the undrained parameters, but indeed, as you say, for final design, you do need more reliable tests, like good quality lab testing data in order to calibrate your parameters and to improve the parameters for final design.